Welcome back, everybody. In today's tutorial, you are going to learn how to code a dueling Deep Q learning agent in PyTorch. You don't need any prior experience. You don't need to know anything about reinforcement learning. You just have to follow along. Let's get started. So, of course, we begin with our imports. We'll need OS to handle some file joining operations. We'll need the base torch package. We will need torch.nn as nn to handle our layers. We'll need nn.functional as f to handle the ReLU function. We need the optimizer, of course, for the atom optimizer, and we need numpy to handle numpy type operations. So the Dueling Deep Q learning agent benefits from a replay memory just like regular Deep Q learning. So we're going to go ahead and code up a replay buffer class. And that just derives from the base object. And that will take a max size, an input shape, and number of actions as input. And the first thing we want to do is save our relevant parameters and make sure to instantiate our memory counter. Now, the memory counter is very important for knowing where your last stored memory is. What we're going to do is we have a memory of finite size. We're going to start from 0, go all the way up to memory size, and then once we try to store memories past that, we come back to the beginning and start overriding our earliest memories. Of course, we need a memory to keep track of the states that we encounter. That will be mem size by input shape, and that will be a numpy float 32. So the star input shape idiom, if you're not familiar with it, this will iterate over a tuple. So we're going to pass in this case, a list, not necessarily a tuple, but we'll pass in a list of elements. In this case, for the lunar lander environment, it is a list containing 8 because there are 8 elements of the observation vector. The new state memory is pretty much the same thing, same shape anyway. It's, of course, the new observations the agent encounters as it takes actions. We need an action memory, and that is numpy zeros by self.mem size. And the PyTorch framework is a little bit particular about data types, so we're going to call this int64. That's really overkill. You're only going to pass in, actions of order, a dozen, 2 dozen or so. So numpy int 8 would actually be sufficient, but it expects long tensors because we're going to use these to do indexing later. So int 64 it is. Numpy zeros for our reward memory, and that gets mem size, and that's float 32. And we need a terminal memory to keep track of the terminal flags, and that gets mem size shape with an uint unsigned int 8-bit integer data type. So numpy int uint 8 means unsigned 8-bit integer, so 0 to 255 exclusive, or inclusive rather. Next, we need to store transitions in our memory. That takes a state, action, reward, new state, and done flag. And the first thing we want to know is what is the index of our first available memory, and that is given by mem counter modulus mem size, and self.state memory index equals state, and likewise for the action memory, reward memory equals reward, new state memory index equals state underscore, self.terminal memory index equals done. Now, and of course you want to increase the memory counter by 1 every time you store memory. Now, in other implementations, I have done 1 minus done. That is great for when you are multiplying by the done vector. In that case, you want the reward for the terminal state to be 0 identically, because once you reach a terminal state, you are expected to your reward is 0 because you're done playing the game. So the terminal memory must facilitate that, but in the case of this particular tutorial, we're going to be using these as a mask and just set every word done is equal to 1 equal to 0. So you'll see that in a few minutes. So there are multiple ways of handling it. No one unified right way of doing it, but I kind of change around depending on which example I'm working with. All it depends on my mood. So sample buffer, self, and batch size. And what this will do is you want to find the maximum memory, meaning the highest occupied position, self.mem counter, self.mem size. So it is the minimum of memory counter or mem size. And then you want to get a batch of random integers, random choice, from 0 to max mem in shape batch size, and replace equals false. That means that you don't resample used memories. So if you sample memory 50, you don't put it back in the pool to sample again. Now this is great for very small memory sizes. If you use a large memory size, it's not such a huge concern, but I put it in here just for completeness. So then states equals self state memory sub batch actions action memory sub batch rewards reward memory sub batch states actions new states action rewards new states, and then done self.terminal memory batch, and then just return states actions rewards new states and the dones. And that is it for our replay buffer. Next we get to the class that encapsulates our dueling deep Q learning agents. So class dueling linear deep Q network. I call it a linear deep Q network because this is not going to be suitable for dealing with the Atari library. I'm saving that for my course. Yes, I have a course, Deep Q Learning from Theory to Code, where I'm going to show you how to go from the paper all the way to the full implementation, and not with the lunar and lander environment, but with the Atari OpenAI library. So for YouTube, we have to suffice with the more simple stuff. Of course, with PyTorch, you want to derive all of your deep neural network classes from nn.module. That way you get access to self.parameters. We want to call our initializer, and that will take a learning rate alpha, a number of actions, a name. The name will be for saving files, for checkpointing, very important, input dims, and a checkpoint directory temp/dqn. And then we want to call super dueling linear deep Q network self.init. This just calls a super constructor. Self.fc1, a linear layer with input dims as input shape and 128 elements for output. So we don't need a very complicated deep Q network to handle this particular environment. So it is fairly straightforward and fairly computationally cheap. .linear, and this takes 128 elements as input and another 128 as output. Now, what makes dueling deep Q learning different is that instead of computing a single quantity for the Q value, you compute both a value function and an advantage function. So self.v will be our value function, and that takes 128 elements as input and 1 element as output. And our advantage is also another linear layer that takes 128 elements as input and n actions as output. And then we take a sum, not a direct sum, but something related to a sum of these two quantities to get our actual Q function. Next, we need an optimizer. That is optim.atom self.parameters and learning rate equals alpha. We need a loss function, mean square error loss, pretty straightforward. We need a device, so if you have a GPU, you definitely want to use it. So that's CUDA 0 if t.cuda.is available, else CPU. If you have two GPUs, you can say CUDA 0 or CUDA 1, and then you can use command line parameters to pass in which GPU you want to use. In this case, I'll just use CUDA 0, self.to self.device, and this will send your entire network to whatever device you specify. And we need a checkpoint directory, and we need a checkpoint file. That's os path join self.checkpointer with name plus, we'll call it dueling dqn. So that way we can have a file for saving our model. This isn't so important if you're running this on a GPU because it runs pretty quickly for the lunar lander environment. But if you're going to implement this for the Atari library, then you'll definitely going to want to save your model file for checkpointing. Next, we need to define the forward operation of our network, and then I'll just take a state as input. So the first layer is just a ReLU activation performed on the feed forward of the state through the first fully connected layer. L2 is the ReLU operation performed on the feed forward of L1 through the second fully connected layer. The value function will just be self.v acted on L2. No activation, we just want the linear output, and likewise for the advantage function, self.a acted on L2. So here we have two parallel streams, value and advantage, that both take the output from L2, neither of which get activated. And we want to return v and a. Very, very straightforward. Next, we have two functions to handle the bookkeeping, the save checkpoint operation, and that just says print saving checkpoint, just so you know it's doing something. Oh, I can't type tonight. All right. What a disaster. All right, so t.save self.state dictionary self.checkpoint file. So this will save our state dict from our model into the checkpoint file. Next, we have the inverse operation, loading a checkpoint, and we say print loading checkpoint, making care to actually type properly, self.load state dictionary t.load self.checkpoint file. So next up, we want to define our agent class. The agent handles the interface with the memory, handles the learning functionality, as well as the functionality for choosing actions, and then it will also handle the functionality of saving the models. So this is kind of a introduction to the concepts of object-oriented programming. An agent is not a deep Q network. An agent has a deep Q network, and the deep Q network is, of course, the function approximator for the state action value function based on the given environment. So just keep that straight in your mind. It's always helpful when you're coding stuff to know how you're going to structure stuff. I've seen lots of examples where they kind of stick everything within one object class, and it's kind of, I don't know, I don't particularly like that because it doesn't make for extensible or maintainable code. So you always want to separate stuff where it makes sense. So the agent is going to take a gamma, which is our discount factor for future rewards, an epsilon, which is the random parameter that determines how often the agent is going to take a random action, a learning rate alpha, number of actions, input dims, a mem size, that's just for instantiating the memory, a batch size, that is for sampling that memory, the epsilon min, so the agent will decay epsilon over time because you want to take more and more greedy actions over time, but you never want it to go directly to 0 because you never know if your model is actually accurate. So you always want to be testing the model with some amount of random actions. And 1% is a good number. You can use 0.1%, 5%. It really varies. It just all depends. Next, we're going to use a linear decrement of epsilon, a factor of 5 by 10 to the minus 7 with every learning step. A replace target of default of 1,000. We use 100 for this particular environment. What this is for deep Q learning, you have a target and an evaluation network, and you only perform the backpropagation on the evaluation network and then update the parameters of the target network every replace iter number of learning steps. So every 1,000 steps, you copy the parameters from Q evaluation to Q next network. Next up, we need the checkpoint directory. Temp/dqn will be our default. Did I do something different up here? You know what? Let's call this temp/dueling, something like that, just to make sure it is distinct from my regular stuff. Dueling _dqn, and we can say the same thing here, dqn, just for consistency's sake. That's just to make sure I'm not overriding any models for the regular deep Q networks. I keep everything in the same directory. So next, we have to store our member variables. Self.gamma equals gamma. Epsilon, of course, is the starting value of epsilon. Self.eps min equals epsilon min. self.epsilon decrement epsilon decrement. We need an action space, and this is a set of all available actions, and that is just 0 up to n actions minus 1, and this will be used for random action selection in the choose action function. We need a learn step counter, and that just keeps track of how many times we execute the learning function. That's related to this replace parameter here. That's so that we can know when we need to update our target network parameters. Self.replace target count equals replace. And then finally we get to the memory, and that's a replay buffer mem size input dims and actions. And we need self.qeval, and that is a dueling linear deep Q network. That is a mouthful. That gets alpha n actions input dims equals input dims. Let's put this on the next line, and we need a name of qeval, let's say, and that is for, of course, saving the model, and we're just going to pass in the checkpoint dir equals checkpoint dir. And then we can do the same thing for the next network. This handles the calculation of the values of the next state, and that gets a different name, of course, q next. But otherwise the parameters are the same. The learning rate here doesn't matter because we're not going to perform back propagation on this network. It's just there for consistency with the interface. Next, we need a function to store a transition in the agent's memory. That takes a state, action, reward, new state, and done flag as input. Self.memory.store transition state, action, reward, state underscore, and done. Pretty straightforward, doesn't return anything. We just want to store a value in the array. Next, we come to the choose action function. That takes an observation as input, and we want to say if np random.random is greater than self.epsilon, then we want to take a random action. Observation equals observation np new axis. This is necessary because the deep Q network up here is going to expect something like batch size inputs, so we're going to pass in a single one with 1 by 8 instead of 8 comma. So nothing too magical there, but we do have to cast the observation from a NumPy array into a PyTorch tensor, and that also has to go to the device of the qeval network, and that is because PyTorch differentiates between CUDA tensors and regular tensors. So if we are performing computations on the GPU, everything we pass in must also be on the GPU. So then blank, we don't care about the value, we care about the advantage equals self.qeval.forward state, and then the action equals t.argmax of advantage.item. We have to call .item because this argmax returns a tensor, PyTorch tensor in particular, and the OpenAI gem only takes integers and NumPy arrays as input for actions. So I take that back, just integers. So we have to call .item to get the actual number out from the tensor. If we're going to take a random action, we want to say action equals np random choice self.action space. This will just choose an action at random from the available actions, and we want to return the action. Next, we have a function to replace the target network, and that doesn't take any inputs, but we do say if self.replace target count is not none, and self.learn step counter modulus self.replace target count equals 0. Then we want to say self.q next load state dictionary self.qeval .state dict, and next we want a function to decrement epsilon. This just handles the decrease of epsilon over time, and we say if self dot, no, we don't need to do any checks there. So we'll handle the check later on. So we want to give the agent some warm-up period, but we'll handle that in the learning function. So self.epsilon equals self.epsilon minus self.epsdec if self.epsilon greater than epsilon min, else self.epsmin. So this will subtract off epsilon decrement from epsilon if it's greater than its minimum value. Otherwise, it just sets it equal to epsilon min, epsilon underscore min. There we go. One less typo to debug when we get to the terminal. Next, we come to the most interesting function of the class, the learning function. And the first thing we want to do is address the question of what happens if we haven't filled up the batch size of our memory. So it's a NumPy array of zeros, and so learning from zeros really isn't helpful. It's not going to give you any useful parameters. So we want to say if self.memory.mem counter less than self.batch size return. So if we haven't filled up at least batch size memory, just return, don't bother learning. In PyTorch, you have to zero out the gradients on your optimizer at the top of every learning step, so that way you don't accumulate gradients from one step to another. At the top of the step, you also want to deal with the question of, do you want to replace the target network? Whoops. Too many spaces. And then you can go ahead and deal with the question of how to actually calculate losses and back propagate them through the network. So we want to sample our memory. So we'll say state action reward new state done equals self.memory.sample buffer self.batch size. So we'll go ahead and sample our memory, and remember that PyTorch requires that we deal in PyTorch tensors, not NumPy arrays. So we have to say state equals t.tensor state to self.qeval.device. These all have to be CUDA tensors. New state, same deal. New state to self.qeval.device. And there's a kind of a very nuanced point here. If you say t.capital tensor, it is a different thing from saying lowercase t. And the difference that I found is that if you use capital T, it will select some default type based on whatever PyTorch thinks you want. Whereas if you use a lowercase, it will preserve the data type of the underlying variable you are casting into a tensor, which is what we want. We don't want to go from an integer to a float 32 because then PyTorch complains. So make sure to use lowercase t for tensor. Just kind of an obnoxious point. It isn't immediately clear by reading the documentation that that is the case. I had to find that out through trial and error. Eval.device. Of course, we don't want 9, we want parentheses. We want reward equals t.tensor reward.to self. I think my keyboard's getting worn out. Maybe it's time to buy a new one. Reward and dones t.tensor done.to self.qeval.device. So this ensures that everything maintains the underlying data type of the NumPy arrays and that they all get sent to the appropriate device. Next, we have to perform our feed forwards. So the value for state S and the advantage for state S equals self.qeval.forward of state. And likewise for the next states underscore self.qnext.forward new state. So we have to do that, and now we have to handle the calculation of our loss function. So in the Dueling Deep Q network, we construct the Q. Notice I'm not saying Q equals forward. I'm saying that the value and the advantage equals the forward propagation of the state and new state through the network. And we have to construct the Q function based on this. So the action value, this advantage has shape num actions, and this is a scalar quantity. So the reason we didn't have to take into account the value function for the choosing actions is because it's just shifting the advantage function by a scalar quantity. So it doesn't really matter. It affects everything equally. It doesn't affect the max. There are a number of ways in the paper they talk about calculating the Q function, and you can read the paper for that. We're going to use one of the ways. We're going to subtract off the mean of the advantage, and that's related to the fact that this thing is only identifiable up to a scalar constant. So you can add a constant to everything, and it's it's kind of like in physics where you can ship the 0-point energy anywhere. It doesn't really matter. So we want to make it nice and identifiable. So we'll say Q pred equals T dot add VS. We want to add the value function to the quantity AS minus A underscore S dot mean along the action dimension. And very important, you have to say keep dim equals true, so that way it doesn't reduce the dimension by 1. And you want to, how many parentheses do I have there? 3. You want to say gather along the batch dimension, gather minus 1 along the action dimension, unsqueeze minus 1, 2 parentheses, squeeze. So we're going to gather up the actions the agent actually took. You can also do a array indexing if you want. I think that works. Sometimes in array slicing can get a little bit confusing, so it's easiest to use this gather, which gathers along, that should be gather positive 1, along the first dimension, the action dimension, the actions unsqueezed along the batch, so that way it's just a linear array, and then you want to squeeze it back down so that it has the appropriate shape. Next, you do the same thing for Q next, T dot add VS underscore AS underscore minus A sub S underscore mean, dim equals 1, keep dim is true. Whoa. 1, 2, 3, gather 1, action dot unsqueeze. No, I take it back. Sorry, we don't want to gather along the actions the agent actually took. It's late at night, don't know what I'm thinking. What we want to do is this. We want to say Q target equals reward plus self.gamma times t.max Q next along the action dimension sub 0, because tmax returns the index as well as the value, and we want to detach that from the network so that way it isn't involved in the back propagation, because this is just a target, it's just a scalar quantity. We don't really want to perform back propagation on anything involved with QNext, because that's related to the QNext network. So very important. Next up, equally important, is to say QTarget sub duns equals 0.0. So what this will do is it'll treat duns as a kind of like a mask, where everywhere the duns, for every index of duns is equal to 1, it will set that index of QTarget equal to 0. The reason you want to do that is because when the game is over, the expected future reward, which this QTarget is the approximation of, is identically 0 because the episode is over and no future rewards follow. Next is the actual calculation of the loss. QEval.loss, QTarget, and QPredicted. The order doesn't matter because it's a mean squared error. To self.QEval.device. And then you want to perform the back propagation. And very important, you want to step your optimizer after you back propagate the loss and increase the learn step counter by 1. And at the end of the learning step, you want to decrement epsilon. So what have we done here? We have effectively done the same thing as in Q learning, except that we have the added twist of calculating the value and advantage, and then when we construct the Q function from those two quantities, we add them together and subtract off the mean of the advantage along the action dimension. Very, very straightforward. It's actually more straightforward than it would seem when you read the paper. So I encourage you to do that. It's a good paper, quite interesting. The rationale behind it is pretty cool. I'll cover all that in my upcoming course, but feel free to handle it on your own beforehand so that you can get a head start. Next up, we want to handle saving the models. And we say self.QEval.save checkpoint, Q next, save checkpoint. And looking at this, no, I didn't make a mistake in my save checkpoint functions. Def load models, self.QEval.load checkpoint, and Q next load checkpoint. Pretty straightforward. Okay, so now let's go to the main function and code up a loop to see that this actually works. So of course the first thing we have to handle is our imports. We want to import Gym for our environment. NumPy, we want to import that so we can calculate the running mean of the last 100 games. We want to import from Dueling Deep Q and Torch, we want to import our agent. We don't care about the replay buffer or the network function. From utils, we want to import plot learning so we can generate the learning plot you saw at the beginning of the video. And of course, if name is main, then env equals gym.make lunar lander v2, of course the discrete version. Games 1000. It only takes 1000 games. This actually learns faster than the regular Deep Q learning. If you run them back to back, you can see that it learns about 50 games faster. It's quite impressive. Load checkpoint equals false. Agent equals agent. Gamma of 0.99. Epsilon 1.0. Learning rate of 5 by 10 to the minus 4. Input dims equal 8. For this environment, number of actions is 4. Mem size, we'll say 1,000,000. Doesn't really matter for this particular environment because each memory is so small you can save 1,000,000 of them. A batch size of 64. An epsilon decrement of 1 by 10 to the minus 3, and a replace iteration of every 100 games. If we're loading a checkpoint, then load models. Agent.load models. That's of course not a function, but we do need a colon. And a file name is lunar lander dueling.png. Scores. Epsilon history. This is so you can see how this score cumulative the score per episode evolves as a function of decreasing epsilon. And we're not going to keep track of the number of steps for I in range num games. We want to set done equal false. Score for the episode gets 0, and the observation is env.reset while not done. Action equals agent.choose action. Observation, say observation underscore reward done info equals env step action. Basically here we're just playing the episode. Say score plus equals reward agent store transition observation action reward observation underscore and done. That should actually be int done because done is a boolean. Let's do that. And then agent.learn. At the end of the episode, you want to, did I call it scores or score history? I called it scores. Append the score for the episode and calculate the average score. NumPy mean scores last 100 games. And the reason that's important is because of the criteria for solving the environment is that the average reward for the past 100 games is 200 or greater. And then you want to just say a little print statement, episode I score 1F. We don't need huge precision. And average score percent dot 1F and epsilon percent dot 2F and percent. Let's go to the next line and we will print score, average score, and agent dot epsilon. Whoa, there we go. Two parentheses, and then epsilon history dot append agent dot epsilon. So that way we can plot it at the end. And at the end of all the games, you want to say I plus 1 for I in range num games. This is just for our axes on our plots. Plot learning, x scores, eps history, and file name. Pretty straightforward. Let's go ahead and head to the terminal and see how many typos I made. So here we are. So I was running it in a different directory, and for my course I had renamed the plot learning function, so the plot was generated in a different directory, but whatever, it's all the same. And you can see this is the end output where it manages to kick ass pretty much through the entire sequence. So if we scroll all the way up to the very beginning, you can see that within the first 20 games it gets a winning score of 200 points and starts to really pick up steam by, I don't know, by 150 games or so, by around 100 and, what is this? I would say by about 135 games, it is almost strictly positive rewards, starting to really pick up steam. So this is a little bit faster than the regular Deep Q network. Of course, there's always an element of randomness in the way the parameters are initialized. So run-to-run differences exist, but it's a significantly faster. If it's 20 episodes faster, that's not insignificant. So let's go ahead and see if I made any typos. So let's just get to it. So Python main torch dueling DQ and lander. No module named torch.nn.function. So let's go to dueling DQ and torch, and that is because it is functional. Save. Try it again. Dueling linear deep Q network is not defined. That is in the actual file there. That's what I'm calling the super constructor. That is because there is a typo. Dueling linear deep Q network. That's because it's dueling liner. No, dueling linear right there. Okay. Agent object has no attribute batch size. That's probably because I forgot to set it. So let's come down to the agent and say, yeah, I forgot batch size. Self.batch size equals batch size. Save. Inconsistent use of okay, that's always the danger of using nano. So let's come down here and get rid of that. Control X. Let's try it again. There we go, and now it is running. Let's make sure it starts to get positive rewards. Yeah, there. One positive reward. Let's see, it isn't doing what I would expect. Let me double check my file real quick to see what's going on. So let's stop this and go back to our code editor and see if I forgot something obvious, because this is clearly not learning. 1 second. Okay, so let's come down here and loss Q target Q pred. So, and I am calling the learning function, and I know it's getting here because it is decrementing epsilon, so it is definitely functional. I'm gonna look at my cheat sheet and see if anything pops out at me. Q pred, Q next, Q target subduns, loss, Q eval at loss, Q target Q pred, loss backward. We are stepping the optimizer. Typically that's the first thing I would look for to make sure I actually step the optimizer. Let's see. VS underscore, yes, mean, reward gamma, T max, Q next, equals 1 detach, Q target subduns equals 0. That looks good. Let me come up to my actual network, blank advantage, turn V and A. So optimizer. Oh, I know what I did. This is stupid. So now this is a trivial mistake. So but it is quite damning. So at every step you want to make sure that you set the old observation equal to the new one. So let's go back to the terminal. Otherwise you'll be constantly choosing an action based on the initial state of the environment, which is totally useless. Let's go back to the terminal and run it. All right, one more time. Oop. So yeah, so it's already starting to dramatically lower the score. In my game 15, it gets 162 points. So it looks like it is learning. I'm going to call that good. Of course, you get some pop-offs, minus 200 or so. So here we go. So yeah, now it's really picking up steam. So that is Dueling Deep Q learning in the PyTorch framework. In my upcoming course, I'll show you how to go from the paper to this implementation, not just in the Lunar Lander, but in the Atari OpenAI gym, so that way we can play games like Space Invaders, Enduro, Atlantis, Breakout, Pong, you name it. We're going to cover a whole gamut. We're also going to couple Dueling Deep Q learning with Double Deep Q learning, as well as the regular Deep Q learning algorithm. So going to be really cool stuff. I'm looking forward to releasing it. That should drop in the middle or third week of September, so be on the lookout. Questions, comments, leave them down below. If you haven't yet, subscribe, hit the bell icon, because I know only 14% of you get my notifications, and I look forward to seeing you in the next video.